Good morning, everyone. Thanks very much for coming bright and early. It is my absolute pleasure to welcome Alex Chen to the stage for his PhD defense. Alex started with us in the fall of 2018. He's a native of the Bay Area and did his undergraduate degree in chemical engineering at UC Davis, where he also got a minor or double minor in English, which has been super helpful in the group, in particular helping lab mates through various medical emergencies, getting their papers back up to snuff, and Alex has really held down the fort in a very important way. So the core research problem of my group for the last 11 years has been the mechanical properties of pi-conjugated polymers. And through that, it's had applications in energy and wearable sensors and lab-on-a-chip devices and haptics. And Alex, in sort of being the steward of that core research area, has been able to sort of spread his wings in these other areas. As sort of a parallel academic career, Alex has also been a real leader in education and promoting access and success of students, where Alex has, for the last 4 years, run the Graduate Application Mentorship Program, or GradAmp, which was recently featured in a first author paper by Alex in Trends in Chemistry. That is one of 7 papers that Alex has written in 2023 alone. He's been on an absolute torrent, and also is kind of an entrepreneur of scientific projects and conjures projects into existence with his considerable creativity, which you'll see on display here. And after Alex defends, he's. Is it confirmed?
It's not confirmed yet.
Okay, but we have a potentially a very nice postdoc offer, and I think we'll hear a lot more from Alex in terms in the coming years. Finally, Alex is the recipient of the Dissertation Year Fellowship, one of, I think, only one engineer who won it this past academic year. And let me make sure that I didn't forget anything I wanted to. Yes, teaching. So Alex has also been a lead instructor for Engineering 15 in our Summer Engineering Institute, as well as the central mentor for the Guided Engineering Apprenticeship Program in Research, or GEAR. As if that wasn't enough, let's welcome Alex to the stage for his presentation.
Thank you very much, Darren, for your kind words. If you say anything else that's nicer than that, eventually my head is going to balloon to the size of Pluto, and I won't be able to exit this door. So thank you all for coming to my thesis defense. This is my 5th year in the Lipomi research group as a chemical engineering PhD. My research focus is on the mechanical properties of semiconducting polymers, as Darren has mentioned. And before we start, I'd like you to please hold your questions until the end of this presentation. I, of course, am hoping that you're going to forget all the hard questions during the presentation and give me some softballs at the end. We've been better at making these transistors smaller and smaller. We've been able to fit a lot more of them onto microchips. And so our microchips have gotten faster while they've gotten a lot cheaper. The other cool thing about silicon and other semiconductors is you can actually control what types of charge move across this gap. For example, you could deliberately introduce impurities that have more or less electrons into the lattice, and this creates a positive or a negative doping. We call these N-type or P-type materials. And if you put P-type and N-type materials together in a junction, something that's very cool is you can get charge flowing across this region, and this gives rise to modern solar cells. But to get silicon into a usable form, there's actually a couple of different challenges. You have to basically melt it, so it's very, very energy intensive. It takes a lot of heat, a lot of electricity, and it's very water intensive as well. You need a clean room environment. Any sort of impurities or dust or particulates or anything like that, they're going to destroy your device. And this process itself is not very environmentally friendly. It creates a lot of pollution. It creates a lot of groundwater contamination if you do things poorly. And when you make things into, say, a solar cell or a wafer with transistors, there are a couple other problems. Silicon is always going to behave like silicon. It's always going to be rigid and brittle. So the applications for which you use these are going to be limited by the mechanical properties. But in society, we do work with a material that we can control the mechanical properties of, and we call these plastics. So you might remember taking an ethylene monomer, and if we connect a lot of these monomers together in a polymer, it'll look something like this. And if we're going to be lazy, which scientists are, we can write it in a shorthand, abbreviated form, or a skeletal form, and this is polyethylene. This is what we use for water bottles, for straws, for plastic bags, basically anything that kills the sea turtles. Semiconducting polymers are a little bit different. If you create a alternating double and single bond motif along this backbone, like you see here, we know that these charges don't actually stay like this. They can actually resonate and float around. So in reality, these charges are sort of smeared across the backbone of your conjugated polymer. And this is called delocalization, and this is what gives rise to the semiconducting properties of these conjugated polymers. The problem is these polymers look something like this when they're synthesized. It's polyacetylene. It's basically brick dust. It's not usable in this form. So to make them more usable, what we can do is, instead of taking this purely conjugated structure, we can add these aliphatic alkyl side chains to increase the entropy of solution. What you can do then is you can dissolve this into organic solvents, and you can use it as is. So we've gotten very, very good at making these polymers. They've gotten bigger and more complicated with a lot of different structures. And the cool thing about this is, like conventional plastics, you can tune their mechanical properties along with their electronic properties. And we have used these for a number of vision applications. For example, flexible solar cells or stretchable transistors or OLED TVs or wearable sensors. So in this sense, we see that the promise of a semiconducting polymer is to combine the electronic functionality of silicon with the mechanical robustness of conventional plastic technologies. And the interest in the mechanical properties of these polymers has changed over the years. In 1989, when we were still working with polyacetylene, people figured out that the transform of polyacetylene is extremely strong and it has very high modulus. This is basically comparable to modern Kevlar, so that's pretty impressive. But in 2007, a group figured out that you can actually co-polymerize P3HT over here with polyethylene, and you all of a sudden get a really, really stretchable polymer film. And not only that, even though you're adding 65% of an insulating portion, when you make transistors, your mobility is still higher than pure P3HT. So that's pretty interesting. And this concept was later applied to organic solar cells. So this is actually work done by my advisor, Darren Lipomi, during his postdoc at Stanford. And the group figured out that, well, if you make stretchable solar cells from these conjugated materials, you can actually get you could get the same device metrics at 15% strain relative to 0% strain. So you can actually stretch these materials quite a bit. And this has given rise to a whole field of stretchable electronics, and we've gotten very, very, very good at this. We have a very deep understanding of how to improve the polymer structure to make these polymers stretchable. For example, you can attach a very stretchable block you could attach a very stretchable insulating block onto your semiconducting polymer. You can also mix things together. You can blend your polymer. And for example, if you blend a semiconducting polymer with an insulating polymer, SEBs, you can create these nano-confined domains that still transport charge while still retaining the mechanical properties of your polymer matrix. And we could think about higher level design too, right? Instead of making these electrodes, so these are gold electrodes, instead of making these gold electrodes straight lines, you can make them curvy in this serpentine design. And this allows for increased deformation of your electrode because it's the geometry that's changing, not actually accumulating stress on your gold itself. But if we think about plastic materials, we have a lot of different things to choose from. For example, saran wrap is very, very stretchy, but once you stretch it, it's not going to return back to its original shape. So it's very plastic. It has very low elasticity. On the other hand, you have something like elastane, like a fabric. This is stuff that you put in your clothes. And it also needs to be very stretchy, but it needs to be able to return back to its original shape. Otherwise, you're in big trouble every time you yawn or exercise or stretch, right? And on the complete opposite end of the spectrum, you have something like Kevlar, which is very strong, very, very tough. And then you have a whole other class of materials, right? You have adhesives. And these all function as adhesives in different ways. So these are all plastic materials, but they all behave mechanically very, very differently. So if we think about the avenue of applications that we have envisioned for semiconducting polymers, right now, a lot of work is being done on wearable devices or sensors, or stretchable transistors, or organic solar cells, or perovskite solar cells, or bioelectronic devices. But this leaves out a whole lot of other fields and applications that are potentially very lucrative, for which the primary mechanical purpose is not the softness or stretchability. For example, glues and coatings and paints, or electronic interconnects, or screens or displays, or polymer binders, stuff like this. And back in 2019 and 2020, we actually took a look at all the state-of-the-art of mechanical properties for semiconducting polymers. And we found that although we've been very good at making them stretchable, for these other mechanical properties like strength and elasticity, we haven't been very good. And this is additionally beneficial because a lot of the characteristics that are associated with these other mechanical properties are also synergistic with charge transport. So today I'm going to be talking about 4 different projects that I worked on during my time in the Lipomi research group. The first one is about the effect of the deposition process on the mechanical properties, and this is work done in conjunction with Kartik Chitari, who at that time was an undergrad and is now is a wonderful PhD student at Stanford. So as we mentioned earlier, silicon, of course, you have to process it from melt, and to process it from melt, you need to heat it extremely hot. And if you're making solar cells, this leads to something called the energy payback time. That is how much energy you need to run your solar cell before you get back the energy that it costs to make it. And of course, if the energy is very high, like you need to process it for melt, the payback time is quite long. So for semiconducting polymers, the nice thing about this is we can actually process these at room temperature from solution. So these are solution processable electronics, and generally we do these by spin coating. So we deposit films by spin coating at the laboratory scale. What this means is we put some polymer solution on top of a substrate of something, of some sort, and we spin it really fast, and this creates a uniform film. So if you're not a scientist or engineer, you might think of this as akin to a potter's wheel, right? But much like pottery, this is a non-continuous process, which is actually a big problem if we're thinking about scaling up these materials for industrial use. Typically, for commercial plastic manufacturing, we do something called a roll-to-roll process. Basically, these giant steel or stainless steel drums roll around and they press together different layers of plastic. But for something like spin coating, where it's basically a start-stop process, you can't do this. So one idea that we had was, let's actually take a look at deposition processes that are compatible with roll-to-roll manufacturing and see how they affect the mechanical properties. And there's a bunch of different ways to tune how your film is made. All we did was we chose films of the same thickness. So to briefly introduce what deposition processes we're dealing with here, solution shearing is also known as blade coating. It's when you have an applicator that sort of guides the polymer solution over the substrate. You have spray coating. think like spray paint, and you have interfacial spreading. And this is sort of a technique that's relatively new. What you can actually do is you can take advantage of the high surface energy of water, and you can drop the polymer solution on top of the surface water, and the film will actually naturally spread. You might think of this as, unfortunately, oil over an oil spill in the ocean. And you can actually take this polymer film and go do other things with it. So to measure the mechanical properties, we use a technique called film on water. So in this technique, because your conjugated polymer is not soluble in water, we can spin a water-soluble layer below it and dissolve that layer so that this polymer floats on top of the surface of water, and we can stretch it. So it will look like this. And from here, we can use the geometry of our dog bone, and we can use the measured load and travel to get a stress-strain curve. And there's a couple of different things that we're interested in on this curve. For example, we're interested in the elastic modulus, which is typically the stiffness or softness of the film. The strength, the fracture strain, which is how much you could stretch it. And we can also separate the elastic versus the plastic properties. So in elastic deformation, your material, of course, can return back to its original shape. In plastic deformation, it can't. The deformation is permanent. So here are our results. We did mechanical testing on each of these, and these are representative curves that are shown. And basically, we can summarize this with the following. Spin-coated films are generally middle of the road. They're no better or worse than anything else. Interfacially spread films tend to be more stretchable than other films. Solution shear films tend to be extremely strong, and spray-coated films are very brittle and weak. So if we were to numerically extract these values from our plot, it looks something like this. But because no one wants to read through this many plots, we're just going to simplify it and go from there. So immediately, we can tell what's happening with spray-coated films if we just look at these films under the microscope. Spray coating causes this granulated sort of microstructure, and you can actually sort of see that in this dog bone below. And this sort of granulated microstructure concentrates stress, and it allows for the fracture of these films very early. So this is why they're very brittle and weak. To look at why the other films behave the way they do, we can actually look under the hood of the car, and we can look at the morphology of our polymer film. So these polymers are semi-crystalline polymers, and what that means is they have crystalline or order domains and amorphous domains. You could think of semiconducting polymer films as having a morphology that resembles spaghetti and meatballs, where you have a bunch of free-floating spaghetti polymer chains in the amorphous domains, and your meatballs are very ordered crystalline domains. And because of this amorphous and crystalline structure, polymers have something called a glass transition temperature. So much like water boils into water vapor at 100 degrees Celsius, the glass transition temperature is the transition between the glassy state of the polymer and the rubbery state of the polymer. P3HPT, which we used earlier, is a low glass transition temperature polymer. What we did to sort of start to investigate the morphology is use a proxy polymer by shortening the alkyl chain length. And by shortening the alkyl chain length, your glass transition temperature goes up. And for the mechanical responses, we actually see the exact same behaviors. Spread films are very, very stretchable, and sheared films are stronger than spin-coated films. So to look at the amorphous morphology, we can use UV vis. We can shine light through this and look at the absorbance spectrum. And by repeatedly heating and cooling our films, we can approximate the glass transition temperature by the thermal transition of the aggregates. And we see that spread films and sheared films both have a higher glass transition than spin-coated films, which suggests a lower free volume and a higher density. Using UV vis, we can also extract the aggregation, so basically how ordered the amorphous domains are. And we see that spread films have very, very low short-range order, while spray-coated films actually, surprisingly, have very high short-range order. Likewise, we could take a look at the crystalline morphology. So we could use a technique called GIXD, grazing incidence X-ray diffraction. So this was work done by Professor Alex Eisner's group at UCSC. And you could shine an X-ray through your film and you can actually visualize the patterns that diffract from the crystalline domains, and you then get something like this. And if you're good at GIXD and can do some image analysis, which I'm not, but unfortunately Professor Eisner is, you can extract some different properties from these diffraction images. For example, you can extract the pi stacking distance, which is how close the backbones are, or the lamellar spacing, which is how far apart these side chains are. You could also extract the texture of your material, whether it's face on or edge on. So by this, we mean whether the side chains are pointing up vertically or whether they're pointing parallel horizontally to the substrate. And we can also extract the coherence length. So from here, we see a couple different things. First and foremost, spread films have a very, very high edge-on fraction, and they have a very high coherence length. Spray-coated films are the complete opposite. They have a very high face-on texture, and they have a very low coherence length. And sheared films have pretty similar characteristics to spin-coated films. So we know that because of the edge-on texture of these films, we should expect charge transport to be better across the film than vertically. Whereas for face-on films, the opposite is true. Charge transport should be favored in the vertical direction. So we can look at the electronic properties of these materials, or in my case, you can stand around unhelpfully while Kardec makes transistors, and you can actually measure the hole mobility of your materials. And we see something very, very interesting here. The mobility of spread films is actually 30 times higher than spin-coated films. So that's pretty cool. So again, over here we see that spread films have the highest mobility. Spray-coated films, despite their poor crystalline characteristics, have approximately the same mobility as spin-coated films. So all of this analysis and characterization allows us to sort of draw a picture of what's happening within these films. So we can attribute the good electronic mobility of solution spread films to this edge-on texturing, which leads to a very high coherence length. But very interestingly, for spray-coated films, it seems like they have pretty good mobilities compared to what we expect from their from morphological characterizations, which suggests that the mobility is actually attributed to the high short-range order, as suggested by aggregation from UV-Vis. So next I want to talk about cross-linking semiconducting polymer films and why this might be useful. So I'm sure by now you must have seen solar farms, miles and miles of silicon solar panels that are laid across the ground. But it might surprise you to know that we don't dedicate very much space to solar energy harvesting. We only dedicate 500,000 hectares out of 81 total million hectares. And why is this? This is actually because rural and urban areas face a juxtaposition of resources. Rural areas that have the space to put these solar farms don't have the electrical infrastructure. You can't transport or store your electricity. But urban areas have the opposite problem. There's no space for solar panels, even though you have a good electrical grid. So you could do a couple different things. For example, you could try to put solar panels above a parking lot. This has worked pretty successfully. Or you could try to put solar panels on the highway or on the road. This has worked unsuccessfully. Don't do this. That's a bad idea. But from this, we could think about all the human transformed surfaces that exist in our society. All the buildings and bridges and concrete surfaces that are covered with anti-abrasion, anti-corrosion coating already, and that are already painted. So our idea was, okay, can we make some sort of photovoltaic paint that we could coat these buildings with, so we could increase the amount of area we could harvest energy from? The problem with this is that these semiconducting polymer films are very thin and very soft, especially if you're using it in a solar cell. And they're so soft, if you have a gloved hand, like you should have in lab, you will actually destroy your film just by running your finger over the film. So they have very poor abrasion resistance. Fortunately, conventional polymers has sort of solved this problem already. There's tires which use vulcanized rubber, right, cross-linked to chemically bonded rubber, or two-part epoxies that are used to laminate furniture or stuff like that. And the way these work is the polymer chains in these materials are cross-linked. So there's covalent bonds that are formed between these long polymer chains. And for semiconducting polymers, this has been explored for a couple different reasons. First and foremost, this enables solvent orthogonality. What we mean by this is that cross-linking your film makes it insoluble. The morphology is frozen. And normally for a solar cell, you have to mix a p-type and an n-type material together. So when you have an insoluble layer, you could actually spin things layer by layer, because otherwise the top layer would dissolve the bottom layer because they use the same type of solvent. In this case, because the bottom layer is insoluble, you can deposit things step by step. The other reason why this has been explored is because when you freeze the morphology, it becomes more stable, especially to thermal aging. So your solar cells can survive longer and they can be heated for a higher temperature and stability. So to look at the cross-linker that we used, in 2020 there was a Nature Communications paper that was published from KAIST, and they reported this 4-armed azide cross-linker, where there's 4 cross-linking sites at each of these armed branches. And they undergo a process called CH insertion when exposed to UV light. And the authors of this paper showed that if you make transistors that are cross-linked, you could actually add about 1 weight % without impacting the whole mobility of your polymer films. So that's what we did. We worked with Professor Nate Romero's group to do some mechanical testing. So Professor Romero's postdoc, Jeremy, synthesized 4BX for us. And what we did was we took a look at all the materials that we had inside our glove box, and we said, okay, let's see generally how the mechanical properties change. So the chemical structures and the names, none of this matters. You don't have to remember any of this. And likewise, none of these names or numbers actually matter. What matters most is these blue bars, which are cross-linked films, are taller than the red bars. And what that means is, in general, over all these extracted mechanical properties, your cross-linked films are more mechanically robust than your non-cross-linked films. In particular, we saw a big improvement for polymers that had a very low molecular weight. So this is DBPC3, and it has a molecular weight of 13 kilodaltons. And we saw that when you cross-link your film, you get a huge increase in your mechanical robustness, in your stretchability, in your strength, in your toughness, which is the energy that can be dissipated. And we can verify this by looking at PDD7. And we compare a molecular weight of 50 kilodaltons and a molecular weight of 85 kilodaltons. And again, we see a very, very big improvement for the low molecular weight polymer, even though, so sure, there is some improvement in the high molecular weight material, but there is a bigger relative improvement for the low molecular weight material. In a solar cell, like I mentioned, you have to mix things together. Your absorber layer is made of a donor material and an acceptor material. So when you have an absorber layer that's sandwiched between 2 electrodes, and light hits this absorber layer, it'll separate photons into electrons and holes. And these electrons and holes will cascade down to their respective electrodes, and this is what causes a flow of electrons and thus current, thus converting sunlight into electricity. And we can characterize these solar cells with something called an IV curve. We can measure the current the device outputs at any given voltage, and from here we can extract the short circuit current, which is how many photons we're able to absorb. We're able to extract the open circuit voltage, the max voltage, and we're able to extract the fill factor, which is basically how square this red line looks. And in terms of efficiency, we could do some basic math, and we can calculate what our maximum power is, and we could divide that by the power that we input, sunlight, and we get a total power conversion efficiency. So we explored a couple different bulk heterojunctions for this. We used 2 types of p-type materials and 1 type of n-type material. So we mixed J51 and N2200 together, and PDB7TH and N2200 together. And first we looked at the mechanical properties, and we saw approximately the same thing. About 1 weight % seems to be the best in terms of optimizing the mechanical robustness. And we made solar cells with these. Or more specifically, I should say we made half-stack solar cells with these. Instead of putting on a evaporated top contact and a transport layer, we used an E-game liquid metal electrode to directly probe what's happening in our bulk heterojunction. And unfortunately, we do see that as we increase the amount of cross-linking we add, we decrease the electronic performance. So the question becomes, if we have this decrease in performance, what do we get out of this? And the answer is we can make use of the mechanical robustness. For example, we can create this sort of janky setup where we drag a sponge over the solar cell, and we see that the cross-linked film survives a lot longer than your non-cross-linked film. We can also make use of the insolubility of your bulk heterojunction. For example, we could throw these in a vat of chloroform, which is a very strong solvent, and we see that the non-cross-linked material washes away, and the cross-linked ones don't. So, of course, your cross-linked solar cells remain stable, your non-cross-linked ones dissolve and are inactive. We could also check the thermal aging of our material, and we see that cross-linked solar cells survive to about 200 hours at 60 degrees Celsius without any sort of degradation, whereas non-cross-linked solar cells degrade below 100 hours. So 200 hours at 60 degrees Celsius, assuming degradation occurs with an Arrhenius function, corresponds to a stability of about 1,000 hours at 25 degrees Celsius. And we can take a deeper dive into the abrasion resistance of our films, because that's one of the big things we cared about. So we could use a sonogator to actually abrade these films with sound waves, and we see that the non-cross-linked film over 60 minutes is basically abraded away, whereas the non-cross-linked film is basically abraded away, and the cross-linked film survives relatively well. And with some image analysis and some UV-vis spectroscopy, we can approximate the film volume that's remaining. And we see that for a non-cross-linked film, we have less than 10% of the film remaining, whereas for a cross-linked film, we have over 85%. So just to quickly summarize, we see that cross-linking is a method that's very, very common to conventional polymers, but we can actually use this to tune and optimize the mechanical properties that we care about, in particular, abrasion resistance. An additional benefit is the thermal aging and the insolubility of your film, but that's already been sort of explored already. So if I was to redo this project, or I was to work on this in the future, I would recommend some stronger considerations about the structure of your polymer and your structure of your cross-linker. Let's talk a bit about the adhesive properties of these conjugated polymers. So this is a solar cell. This is a flexible organic solar cell. And you might notice that, like onions and ogres, solar cells have a lot of different layers. And this leads to some very interesting problems. First and foremost, your semiconducting polymer film is in this solar cell because it needs to conduct charge. It needs to transport charge somewhere else through this device. But unfortunately, this also means that your polymer film must hold together the layer that's below it and the layer that's above it. In this sense, it functions as an ersatz adhesive. So it's an adhesive even though its primary function is not primary function is not intended to be an adhesive material. And work by a previous graduate student, Dr. Mickey Finn, and her group built this torsional machine where he got this solar cell and he twisted it a bunch. And he found that, well, after thousands of cycles, you actually get the lamination of these solar cells at the P3 GPCBM and P.PSS interfaces. So we set out to sort of have a deeper understanding of what's going on here and how we could potentially improve the adhesive function. So again, we turn back to our favorite monopolymer, poly3-alkyl-thiophades. And this time, instead of using one or two, we have an entire library of them where we're varying the side chain length. We're gradually increasing the length of this alkyl group. And previous work has already looked at the mechanical properties of these. And in general, as you increase the alkyl chain length, your modulus gets decreased, and that's because your glass transition also decreases relative to an increase in the side chain. So after some mechanical testing, we see some pretty interesting things. We can summarize them as such. The elastic behavior of these materials is relatively monotonic. So we can imagine, of course, these polymer films behaving like springs. And the longer this side chain is, the better it functions as a spring. You can stretch it further and further without plastically deforming it. But plastic dissipation of energy instead of elastic storage of energy requires a trade-off. And we see that, in particular, the best fracture strain is not at the longest side chain length, like you would expect. It's actually at n equals h, so P3OT over here. You could think of this plastic behavior as, of course, behaving like saran wrap. So we worked with a collaborator at Arizona State University to sort of understand what's going on here. So we used nano indentation to compress these films and measure the mechanical properties. And while you're doing nano indentation, you can actually oscillate this indenter, and from there you can extract the loss modulus, the storage modulus, and the tan delta. And you can think of these as, for example, if you bounce a tennis ball from a yay height and you drop it and it ricochets back up, the amount of the height that it returns to is basically the energy that was stored. And the difference between the starting height and the final height is the energy that was lost from heat or friction or anything else. And we actually see that the highest viscoelasticity is at n equals 8. So the best viscoelastic properties is, again, not at the longest side chain length, it's at n equals 8. So we can start to characterize the adhesive properties. Now we can do a couple different tests. First and foremost, we can do a shear test. And in a shear test, we basically sandwiched these polymer films between two glass slides, and we pulled it apart. And from here, and we also did peel tests in which we put on a piece of tape and we just ripped it off and saw how much force it required. And after some normalization, we found that again, the greatest adhesive properties are associated with P3OT, a polymer that has a side chain length n equals 8. Of course, for these adhesive materials, for these semiconducting polymer materials, you aren't going to ever basically put them on a glass slide and just use them as such. As you saw in the previous presentation, we actually have different layers that go below it and above it. So in the case of a solar cell, you might be interfacing with P.PSS, which is used as a transport layer. So what we decided to do is we did some more peel tests, and we decided to put them on top of P.PSS. And interestingly, we see the debonding behavior actually changes relative to the side chain length. At P3BT, which is the shortest side chain, you get delamination between the tape and the P3AT layer. For all the other ones, you get delamination between the P3AT layer and the P.PSS layer. And then finally, for P3OT, the longest side chain, you again get delamination between the tape and the P3AT. So why is this happening, right? You have materials that are on the opposite ends of the spectrums, and they debond the exact same way, but clearly for different reasons. So what we did was we looked at the surface energy using contact angle measurements, and we saw that as your side chain increases, your surface energy decreases, which suggests a trade-off between how well your material can adhere to the bottom layer and how well the tape can adhere to the P3AT layer. So P3OT in particular represents a transition where it eventually becomes unfavorable for the tape to stick to your polythiophene layer, and thus you get debonding basically at two different interfaces. Your material wants to rip off both at the P3AT tape interface and at the P.P3AT interface. So this taught us a little bit about the adhesive properties of our materials, and we saw that increasing the side chain length generally increases the elasticity of your material, but this unfortunately doesn't represent a good strategy for in terms of stretchability if you want to make a stretchable polymer. One common method that chemists use to increase the fracture strain of these materials is just to make a side chain with a longer, basically a longer side chain. But we showed that this eventually has diminishing or unfavorable returns. Furthermore, if you're engineering your polymer, you have to consider how it's going to adhere to your bottom layer as well as your top layer, right? So, for example, something that this might be important for is designing a polymer with better functional groups and better functional side chains than just an alkyl chain. So we talked a lot about some very, I think, basic and fundamental studies over here. So the question that you might, of course, have is, well, how do you actually apply this in real life? Like, what is this useful for? And that brings me to an ongoing project that we have in the group, which is silver-free conductive adhesives for shingled solar cells. And of course, you might know that solar cells have gotten a lot cheaper over time. They've gotten very, very cheap. In fact, they are cheaper than all other sources of renewable energy and many sources of petroleum-based energy. That being said, you might notice this little green sliver over here is how much solar energy powers our electrical grid. And you might notice that's like 2 to 3%. That's not very many. So how do we reconcile this? Solar energy is the cheapest it's ever been, and it's cheaper than all other sources of energy, but we don't use any of it. Actually, a lot of these problems are associated with socioeconomic policy and politics. So if you're an undergrad who wants to work in renewable energy and wants to make the world a better place and make sure your kids don't drown as the glaciers melt, you might actually want to consider a career in politics. That might actually be more beneficial. But as scientists, all we can do is sort of make solar cells better and cheaper. And that has been relatively successful. As the cost of solar panels has gone down, we have installed more and more solar panels and more solar farms. So our goal as scientists and engineers is to make this red line go down and that yellow line go up. And there's two ways to do so. You can improve the efficiency of your devices, or you could decrease the cost of your devices. However, we run into a problem. We can look at the efficiencies of modern solar cells, which is actually kept track of by the National Renewable Energy Laboratory. And we can look at a couple different classes of materials. For example, normally I work with a class of photovoltaics called emerging photovoltaics. These are organic photovoltaics or perovskites. And you can see that the efficiency of these devices has increased very, very quickly. Perovskites 10 years ago had a maximum efficiency of about 13%, and now they're at 26%, so it's doubled in 10 years. But silicon, unfortunately, doesn't have that trend. A lot of silicon seems to have flattened out in terms of efficiency. So why is this? It turns out that for any sort of material, there is a thermodynamic limit for how efficient your device can be made. For silicon, this is about 33%. And considering for commercial cells, we're already at about 25 to 27%. We're already pretty close, right? So this means that any sort of increases in efficiency or decreases in price generally have to come from module architecture and design. So this is what a modern solar cell looks like. You might have solar panels on your roof or your parents' roofs or anything like that. And you might notice that these solar cells are connected by these solar bus bars, these metal interconnects that are heated really hot and then basically drawn onto these solar cells. And these bus bars are usually copper. And you might notice that this requires a space between these solar panels. So this is what I'm going to refer to as the conventional architecture. In comparison, you could do something called a shingled solar cell. And basically, as the name suggests, much like rooftop shingles, you could basically overlap them and glue them together. And you might notice that there's no space between these cells compared to these. And this is pretty good, because this means it leads to a couple different trade-offs in efficiency. For example, it can improve the efficiency by increasing the amount of surface area. There's no bus bars to cover your solar cells, and there's no spaces in between your solar modules. You also get decreased shading losses, and because you don't have to heat your metal really hot to glue them together, you can actually have a less expensive manufacture process. So we talked about the energy payback time. This sort of ties into that. So the things that we use to glue together these solar panels are called electrically conductive adhesives. And what they're made of is they're made of silver particles that are encapsulated in epoxy. So it's basically a plastic glue that's filled with silver. And the silver, of course, creates a conductive pathway, but this leads to a couple different problems. first and foremost, you need about 70 to 80 weight percent silver. That's a ton. That's a lot. So it's a very, very expensive. And silver doesn't really just appear in your lab, right? It has to come from somewhere, and it has to be mined. And this has a huge environmental footprint. It contaminates groundwater. It contributes to deforestation. There's also huge ethical problems in terms of exploitation of labor. And the other problem is that these two materials want to do different things. The silver wants to conduct electricity and not stretch, and the polymer matrix wants to do the opposite. It can stretch and do whatever, but it doesn't want to conduct electricity. So this leads to some mechanical trade-offs. For example, as your devices heat and cool over years and years and years, you might get migration of these silver particles into giant domains, and then your pathways, your electronic pathways, are no longer connected and no longer percolated. What you might also get is, for example, crack formation between the silver and where the silver meets the polymer chain. But under the under the ruthless fist of capitalism, all we really care about is the actual cost. And for commercial conductive adhesives, you're looking at a price of about $2 per gram, but copper is about a fourth of the price of that. So even though you have to factor in a more expensive manufacture process that involves heating your material, it still ends up being cheaper than your conductive adhesive. So how can we design our way around this, right? This is sort of where semiconducting polymers can come into play. Our central hypothesis is, well, what if you didn't have an insulating matrix, right? What if you replaced your insulating matrix with a conducting matrix? So the idea is, if you replace it with a conducting matrix, you need to add less things to make it conductive. You increase the electrical percolation pathways that are in your glue, and you don't need to add very much stuff. So we're working with a conductive polymer called P.PSS, and previous work from our group has shown that you can actually modulate the mechanical properties of these conducting polymers by copolymerizing this PSS block with a long and soft side chain. And our two central goals here are, of course, to replace or reduce the electronic filler, and also to reduce the cost. So we can immediately see how we're doing with number 2. P.PSS is not a scaled polymer right now. It's used in laboratory and research scale applications. And even so, I buy P.PSS for about 65 cents a gram, which is less than half the price of a conductive adhesive. So immediately we see potential room for improvement, right? This means that we can potentially scale this material for larger use. And previous work by our postdoc, Dr. Rachel Blah, has showed that if you attach this stretchable stretchable insulating block, you can also improve the adhesion of your solid film. So we started looking at P.PSS, and what we did was we added some stuff to it to try to improve the electronic properties. So we added these polar small molecules, DMSO, glycerol, ethylene glycol. We added this polyethylene glycol, and we added multi-walled carbon nanotubes. And over here is the bulk resistivity of our material. And we actually see that the polar small molecules outperform the carbon nanotubes. So this is actually pretty cool. This means that we might not even have to add electronic filler. The reason for this is pretty well understood. It's because the small molecules interact with the morphology of the P.PSS film in such a way that it improves the electronic pathways. You might think of this as, for example, baking a cookie, where you're adding chocolate chips to the end. In this case, the analogy is the chocolate chips of the carbon nanotubes or the electronic filler. And in that case, all you're trying to do is incorporate the material. But in the case of these small molecules, it's like adding sugar to egg, where you're actually creating chemical changes within your mixture. You can tell that I haven't had breakfast yet because all my analogies are now food-related, unfortunately. So to use these materials for shingling, you obviously have to control how much you dispense and where you dispense it, right? And this is sort of one of the challenges with P.PSS. It's about 1.3 weight percent of solid material in water. It has a very low viscosity. So if you deposit it on a silicon solar cell, it's going to spread. So this is work done by my undergrad Sarah, and what you can actually do is you can evaporate some water out, and you can increase the viscosity to get a better dispense line. And we saw that about 10 pascals a second gives us a pretty clean dispense line. So we worked with a commercial group to shingle solar cells, and what they did was they took these commercial sun-framed solar cells and they laser cut them, and they glued them together in comparison to CA183, which is just a commercial standard. It's a standard 70 to 80% silver in epoxy sort of material. We see that for PEDOT-PSS by itself, because it has a very low conductivity, it has a very poor bulk resistivity, the series resistance is extremely high, and the cell is very bad, right? You can remember that we care about how square this blue line is. Well, this is not very square. It doesn't look very good. But the moment you add DMSO as a small molecule dopant, your fill factor is largely recovered. And we can compare the fill factor between the two, and we see that actually they're very, very close. For the commercial standard, that's silver and epoxy, you have a fill factor of about 72%, something like that, whereas PEDOT-PSS, you can actually achieve a conductivity of about 71%. Of course, we also care about degradation mechanisms, right? Because these cells are going to be exposed to heat and light continuously, so they're going to heat and cool repeatedly. So what our colleagues at D2 Solar did was they made these solar cells, and then they held them at 85 degrees Celsius for 3 hours. And after that, they measured the IV curve again, and we don't really see much change again, which is pretty impressive. The problem we are running into is the mechanical performance. The adhesion is relatively poor. You can see in all these colorful colors, these are commercial standards that we're comparing against. And PEDOT-based materials are down here, which unfortunately means that the adhesion is pretty poor. So right now what I'm working on during the rest of my time here in the group is actually trying to solve this problem. One of the approaches we're taking is we're blending PEDOT-PSS with this commercial polymer, polyurethane, which is commonly used in adhesives and coatings. And we're trying to use a blend to manipulate the adhesive properties without drastically decreasing the electronic behavior of the material. So just to quickly summarize, we have conventional silicon solar cells that are already very good, but one way to make them better is to shingle them together like rooftop shingles. And instead of using silver-based conductive adhesives, we can make all polymer conductive adhesives that have a similar electronic performance, but are way, way cheaper. So that presents a potential avenue for actual commercialized products. The current deficit with these materials is their adhesive properties, which is something that we're working on right now. And before we wrap up this study, another thing that we're working with D2 Solar is we're studying the module degradation, and we're going to be doing a sort of detailed economic analysis to see whether this is actually a good approach forward. So just to conclude my entire talk, this is a figure I made. I really hope the future looks better than my PowerPoint skills. But what I hope to convey to you with this is that semiconducting polymers offer potentially many lucrative applications, particularly within energy, that can potentially be beneficial. And we have to actualize these applications by rational consideration of the mechanical properties of these materials beyond that of just stretchability and softness. So these are the papers that I've worked on during my time here. I'd be happy to talk to anyone about any of these things. And our group is very interdisciplinary. It's very collaborative. I've been very, very fortunate to work on a number of collaborations, not just in energy, but outside in bioelectronics as well. So we have a ton of work by some wonderful and very talented PhD students and postdocs over here. And during my final couple months, I'm going to be trying to wrap up a couple different projects, or helping other people wrap up a couple different projects. So that's the end of my presentation. There are so many people that I have to thank. It's absolutely ridiculous. So thank you to my committee for being here. Chen, Nathan, Zheng, David, and Darren. Thank you all for being a wonderful committee. Darren, I have no idea how I would have done this without you. Thank you for being a wonderful advisor and friend. David, who's online. I've been working with David for the past couple of years now, and he's basically my unofficial co-advisor. Working with you has really improved how I think about science and think about photovoltaics and all this other stuff. So I'd really like to thank all the wonderful people that have provided me advice. Of course, the Fedi group, who I spend a lot of time at 311 and just to distract everyone, and I have always had a lot of fun visiting and chatting with everyone there. The Lipomi Research Group, of course, there are so many people that have positively influenced my research career. I've had a wonderful undergrad team that's made all this possible, and without all of these collaborators and all these different teams, I would not have published a single paper. Staff, of course, they're the people that actually run this department and make everything happen. Dana, G, Zuchi, thank you so much. I'd like to thank all my wonderful SME neighbors. And as Darren mentioned at the very start during my introduction, I've had the fortune of creating a academic program here at UCSD called GradIP. And so I've had the opportunity to work with Darren, who wears many different hats in a number of capacities, both as my advisor and as assistant or associate dean for students. And lastly, I'd like to thank my family. I could not have done this without any of them. So, thank you very much. That's it.